Hell yeah. All right, so math makes logical sense, and then when you get an equation that doesn't make logical sense, it melts my mind. And so this is surveying, and surveying is a class where it's difficult enough. And then to have an equation that doesn't make perfect sense is mind melting. And so, anyway, so here's the equation for corrected length. You know what I mean? We're using a steel tape that a lot of things are off. You know, its length will say 30 meters, but it's actually a little bit off. It's not, but that should be that the general gist of it is that length should be hopefully fairly accurate. You know, if it says 30 meters at its standard, you know, or at some base, like that needs to be known. And even if it is off, you can figure out what that length actually is, maybe, you know, by you know, getting it measured like 100% or whatever at specific temperatures and stuff like that. So the corrections for this are always taking the measured length. So you're going to use that tape and you're going to measure something. And then what you're going to do is you're going to correct for temperature and then maybe the tension that you pulled on it. But when you correct for temperature, you're using that measured length. And for material mechanics, you don't do that. You use the original length. And so, and that's just really fascinating to me. So what they're doing in surveying is they're using the measured length and they're just hoping that's accurate enough, you know, to do the temperature calculation, which is pretty minor. But I finally pulled up a Google AI that says, you know what I mean, you should be using the most and best accurate length. So it says if the tape is inaccurate, so if there's error in the nominal reading, like due to the instrument itself, the tape measure has stretched over its time, that error is going to exist regardless of the temperature. And so, let's see. The most logical and accurate procedure is to ensure the value you are using in your calculations, the length measured in your formula, is the most accurate value. So that, I'm so glad they mentioned that here, because this formula is just saying, hey, you measured a length, but yeah, you measured a length with a piece of junk. You know what I mean? We know that it has an accurate measurement of some sort of temperature, pull, and all that, but you had it sagging, you had it, you know, even the fact that you're going to sag a steel tape, you're going to be in a different temperature, and then its measurement actually is going to be wrong. It says 30 meters, but we know that someone actually measured it and it's 30.01 meters, or it's going to be less than that, but, you know, it's going to be 3 millimeters off or something like that. But hell yeah. And then so why would you use that wrong length when calculating the thermal expansion? So that's fascinating to me. But maybe this equation, no, it doesn't, because the other piece of this is the C. I don't even know if I have it. Let's see. Yeah, so C standard is where, you know, like for this one, they said, hey, the steel tape is actually, you know, if this is in meters, then a decimal place would be 10 centimeters, then a centimeter. So this is 3 millimeters off. So for every 30 meters, this tape's 3 millimeters off, and they know that. But on the reading, when you read 30 meters, you're going to, you know, calculate, because you're going to use it as a tape measure, and you're going to be like, cool, I wrote down 30 meters every time I use that length. And so when doing and then you just measured 605 meters using that 30 meters, but when you do your temperature calculations, you're going to use that 605 for the temperature. You're going to use this measured length for the temperature, when you should have, you've already done the calculation for, because you know it's 3 millimeters off for every 30 millimeters, well, you did 605 divided by 30, so you have about 21 of these, you know, 3 millimeters. And then so, yeah, you're going to be 60 millimeters off. And so now we know that the actual length wasn't 605, it was 605.0605. So why the heck would you not use that number into this thermal expansion? You know what I mean? And if you're, I mean, it's so easy to be like, hey, this is going to be a first, second, third, you know, when it comes to this formula. You're going to do the C standard first. You know, if you know that there's a nominal, like however you say that, is nominal like what it actually marked. Like if you're calling that nominal, that's what I was going to call as nominal. What do they call it? Ooh, I lost it. Oh, my bad. But hell yeah, because you have like either just the actual, you know, I lost it. But anyway, so but you have this, you know, if it says 30 meters, I'm going to call that nominal, but the actual length is 30 meters and 3 millimeters longer. And so you're going to do that calculation first. You're going to take your measured length of 605 and then do your change due to the fact that your things, you know, you mismeasured it. And so, and then that's going to give you your first correction. And so if that's all, if you don't have any change in temperature from the standard and you didn't pull on it, you just laid it on the ground, then that will be your true length. So why not then use that into this equation? Because this equation, they're just using this measured length. So that's the general gist in another 5 to 6 minutes to just, you know, but I actually got a little bit more insight into this, and I can see where I could, you know what I mean, from just a perspective of like, yeah, you're trying to use the most accurate representation of the length when you're using these. And because, yeah. And even with that, I still think this is wrong. Because from the material mechanics perspective, you always use the original length. Well, I don't know. No, it says, no, well, there is a, well, I don't know. I was trying to figure this out. The final length is the original length plus the change in length. The original length plus the change in length, which is calculated as the original length multiplied by the coefficient of thermal expansion. So yeah, with coefficient of thermal expansion, you have to measure the length before it expanded. Because it's a proportion, you can't just double the length of something one way. But I have to look this up mathematically, because I didn't ask this question right. Mathematically, because it's proportions, you can't just use the length after thermal expansion and then add that you can't have something had a base temperature of 20 and then you're at 35 degrees and you would expect thermal expansion and use the measured length. Well, you would have to subtract it. And then, yeah, your change in temperature would be your change in temperature. Oh, that's kind of interesting. But yeah, this length, see, that's where, from material mechanics, this length measured is the original length. And that's the difference. And that's crazy with the surveying. They're measured the final length. They're going to measure the length and then say thermal expansion happened. And then you'd have to run this equation in reverse. But I just think mathematically it's not accurate that way. But maybe it is. That was the question I was trying to ask. So maybe I'll throw some numbers at it and see if I can come up with a mathematical error. Just because I thought it used proportions. You know what I mean? If you move proportional, I have no idea. So anyways, I'm going to be done with this, but that's good enough for me. But yeah. Equations that aren't just like where they're totally spelled out, where you're just like, what are you doing? It drives me nuts. I think surveying is the worst too, because it's like, I'll just end with this. You should always be in surveying thinking of the big picture. I got in trouble, getting horrible data that maybe I could have caught, if I was just paying attention, forest for the trees types of stuff. All right, hell yeah.